My constraints and objective function are basically based on those provided by the document, but I did some improvement and necessarily change. Well, at first, this is my Excel spreadsheet model. On the left side, this part are all the data showed in the problem described. I put them all together to make it easy to find them when I'm modeling this problem. Then we can see the right top part. And here are all the variables I used to modeling this problem. And those yellow cells are decision variables. And the bottom side, this part is the profit and the cost part. I divided them to many different parts to show more details, include the rent profit, the undamaged and undamaged car transfer cost, the opportunity cost, and the repair expand fixed cost. Next step, I will explain my constraints and objective function. What needs to be explained in advance is that in Excel and LPserv, I use the same constraints and objective function. The only difference is in Excel, I have all the variables when I equal to j, while ij represent depart. While in LPserv model, I didn't do that. I didn't identify those variables which represent the number of cars transferred from a depart to the depart itself, which is unreasonable in the problem. While in Excel model, I set those specific variables as a very large number to avoid those unreasonable situations happen. Okay, now I will show all the steps I identified in the screen to make my constraints easier to understand. Let's start from the constraint 1. This is my constraint 1. Here, it represents the number of undamaged cars at the beginning of each day, namely show what happened between step 1 and before step 4. Then what happened in the next day is represented by constraint 3 here, namely from step 4 to the end of the day. And also we can see the constraint 2 and constraint 4 they are similar to the constraint 1 and 3, but what then described is the change of the number of damaged cars. What is important is because I try to do not modify too much constraint expression of the instruction document, so I set counting the number of damaged and undamaged cars at different time period. Well, when I work in the constraint 3 here, I made a little change than the constraint 3 provided by that document because I notified that here the marked part is redundant and it has included in constraint 1 here. So I delete this part in constraint 3. And also because the constraint 1 and 3, the constraint 2 and 4, those two groups representing the same variable separately, so there would be two equal expressions between them, like here and here. Which should be clarified is because the company will close on Sunday, so I said the next day of Saturday is the Monday. So in order to make those 2 days, those 6 days become a circle. Now let's look at the constraint 5. here. It represents the repair capacity limit of each part on each day. Clearly, the number of repaired cars each day cannot exceed the repair capacity. And the next constraint is the demand limit of each part. The demand limit of each part should more than or equal to the number of cars rented out each day. Then the constraint 7 here is the total number of cars. I do another change on the original constraint 7 in document because I didn't fully understand what it means. Well, in here I choose to calculate how many cars the company have on Tuesday. So this expressions This expression means all the damaged and undamaged cars in each depot on Tuesday, plus all the cars have rented out 2 days ago or 3 days ago, which haven't returned to any depot on Tuesday. Because when I count the NU and ND variables, those two variables, all the cars rented out yesterday, which only rent for only 1 day, already have returned, and those cars transferred between depots have arrived destination too. So I will not count those cars. Now we can look at the constraint 8. Here. This is the last constraint, which includes 3 little constraints, and all of them are work for the expand repair capacity option solution. I set 5 binary decision variables, as we can see in this yellow cells. I set those binary decision variables to represent if we choose this option or not. The option when these variables equal to 1, which means I have chosen this option. If then equal to 0 means I didn't adapt this option. Of course, as the problem described, I can only choose not more than 3 options in total, like here. Well, now I will show the setting of my Excel OpenObserver. I set the integer optimality to 0 to make sure that I can get the best solution. And here, I'm looking for the maximize profit, so this button I choose maximize, and all my other constraints shows here. The compact expression of objective function is too long, so I will explain it using my LP-Observer model. Well, let's try to solve this model. Here is my solution. This is the total number of cars that the company holds, and this is the profit. Now let's see my LP-Observer model. I separate the objective function to 10 parts because it's very long. And the function of each part I have written down as a comment. So we can see here. In this LP-Observer model, all constraints are the same as in Excel, and they are even in the same order. We can see this is a constraint 1, and this is a constraint 2. Well, And I won't repeat them again. Because the LP model has so many data and it's very long, I use star programming to help me to input those expressions. Well, now we can look at the answer. Here, we can compare the answer of my LP-Resolve model and my Excel model. And we can see this is the profit, this is the profit, this is the total number of cars, and this is the total number of cars. They are very similar. So that's all my presentation. Thanks for watching.